Greetings, this is Brian, and I'm speaking to you from a studio in the basement of the Clark Building, and this is an unusual way to present the lecture. I'm speaking in a soundproof booth, but typically I'm sitting in a room with 250 smiling faces. It's a bit different, but I'm going to try to give you something very close to a lecture experience, something very similar to what you'd experience in the Physics 122 class, and today we're going to be talking about electromagnetic waves. Now, our first topic with electromagnetic waves is this. Electromagnetic waves are traveling waves of electric and magnetic fields, and we're going to talk about implications of that today. But before that, I want to talk about how I want you to use this video. And that's this. I want you sitting at home, I want you to download the notes as you would normally. I want you to go through the slides as you would in class. And when I say I want you to pause the video here, and I want you to try this calculation yourself, I want you to pause the video and try the calculation yourself. The important point isn't that you can watch me do physics, it's that you know how to do physics yourself. So try the things through. And as you're doing that, talk to your friends. You can reach out to them virtually. You can actually watch this lecture with other people if you're comfortable doing that. And then, during the time of classes, we will have TAs, learning assistants, and me standing by. We will have people standing by to answer the questions that you have. So go ahead and work your way through the problems. And when I say we'll walk among you and advise and critique, I don't really mean that literally, but what I mean is we will be there, and if you want to weigh in, we will advise and we will critique. There are people standing by to help you through this. So even though you're doing this on your own, even though you're doing it virtually, I want you to treat this as close as possible to how we would normally do the Physics 122 class. Let's dig in. So our first piece of the puzzle is this. Electromagnetic waves, we can use these to send energy through space. I saw something like that, or you've seen something like that with wireless charging. If you have ever seen a device like this, you can put on your bedside table, you can charge your phone, you can charge your watch, you can charge your earphones. You do that by transmitting energy from one place to another. That's wireless charging. But there are systems being developed that can take that a lot farther. Here's a system that transmits power from this coil over to this coil right here. And it's actually transmitting it through the heads of the people standing in the middle. Apparently, they're experiencing no ill effect. And this wireless power is going to be something that you will see in your lifetime. You will go to a place where you can sit and you can work on your computer, and they'll offer Wi-Fi. You're going to want Wi-Fi for sure, but you're also going to want Wi-Po. You're going to want the wireless power. You will demand that. That is coming. And the way it's going to work is with electromagnetic waves. Now, we saw in class the day before spring break this thing where I was running this big 1,000,000-volt Tesla coil, and it was sending energy out through space in the form of electric and magnetic fields. And as it did that, people could hold up light bulbs, and those light bulbs would light. So you've seen the phenomenon of wireless power, and it's related to the topic today, which is electromagnetic waves. And we're going to start our discussion of electromagnetic waves by talking about the long wavelength end of the spectrum, such as microwaves and radio waves. Now, the microwaves, the micro piece doesn't sound like it's long wavelength, but they're much longer wavelength compared to visible light and other waves that we'll see. Now, I'm going to start with a question. So it turns out the frequency of radiation emitted by a cell phone is about exactly the same as the frequency of radiation emitted by a microwave oven. Your cell phone emits about 0.6 watts of electromagnetic waves, and they actually are microwaves. They're almost the same frequency. So you're transmitting microwaves. They're being absorbed by your head. Question, should you be worried about this? And the answer is no. And we'll talk about why. We'll come back to that point later. Now, today we're going to talk about the properties of electromagnetic waves that have to do with their wavishness, their wave properties. There's also ways in which they can look like particles. That's something we'll talk about in the next class. Now remember, we talked about this idea that if you have a changing magnetic field, it induces an electric field. And this was also discussed in the chapter. And actually, a changing electric field induces a changing magnetic field as well. And this fact, that a changing magnetic field induces an electric field, and the changing electric field induces a magnetic field, is, honest to goodness, one of the coolest things ever discovered. It is responsible for the fact that I can deliver this lecture to you through the air. it's being delivered via the very phenomenon that we're going to talk about today. This is kind of a remarkable thing. Now, there's these equations that unify electricity and magnetism. Everything we're going to learn in this electricity and magnetism section of the course can be summed up by these relationships here. These are known as Maxwell's equations, after James Clerk Maxwell, shown here in this photo with his somewhat severe-looking wife and his somewhat weird-looking dog. Anyway, Maxwell has these 4 equations. This one here is basically Coulomb's law, okay? All the rest of them have to do with basically encapsulating everything we've learned about electricity and magnetism. It's all here. But if you take those 2 equations and 4 equations and use for these constants, which you know together, it predicts the existence of electromagnetic waves. And so if you have a charge and you quickly accelerate it, so imagine taking this, move it to the side, it sends out a pulse of electric and magnetic fields. And the pulse should travel at this speed. Maxwell's equations say, well, if we put in these constants, you know what epsilon 0 is, you know what mu 0 is, you get a speed of 3 times 10 to the 8th meters per second. This is AKA the speed of light. And so people, when Maxwell discovered this, said, could it be that in fact light is a wave of electric and magnetic fields? And it turns out that is absolutely true. And that's our topic this week. So we've got this electromagnetic pulse, but you can also have electromagnetic waves, and they are waves of electric and magnetic fields. So if you stand at one point in space, the electric field will get bigger, and then it will get smaller, and then it will get bigger, and then it will get smaller. Same thing with the magnetic field. It will be getting bigger and smaller as well. Now, it's not the fields themselves don't move. It's just that the fields will grow at one point in space and then they'll shrink. So if you stand at one point, if I imagine standing at this point in space right here, the electric field gets bigger, smaller, bigger, smaller, bigger, smaller. If you stand at that point, it's going to look like this. I'm standing right here. Electromagnetic wave is coming towards me. There's a big electric field. There's a big magnetic field. And then sometime later, what's going to happen is this. There will be a smaller electric field and a smaller magnetic field. And then sometime later, if you're standing at that point in space, there will be an electric field in the opposite direction and a magnetic field in the opposite direction. And then sometime later, there will be a bigger electric field in the opposite direction and a bigger magnetic field in the opposite direction, and so on. So if you're standing still, the electromagnetic wave is bringing electric and magnetic fields to you. They will change from big to small, they switch directions, etc., etc. Now, this is a picture from the textbook about how the waves look. And the important thing I want to note is this. This is a picture, and the electric fields are along the y-axis. If this is true, we will say this is the plane of polarization. The waves are vertically polarized. The electric fields are along the y-axis. The magnetic field is along the x-axis. That's an important point we'll come back and talk about later. At one point, as you sit there, the fields change. But here's the thing to know. Electromagnetic waves are waves. They are waves, and so everything we've learned about waves applies. The only difference is the speed of the waves is the speed of light. And so our basic relationship for all waves, which looked like this, v is equal to f times lambda, now turns into this equation. The speed of light is equal to f times lambda. But as with all waves, the frequency is proportional to 1 over the wavelength. Oh yeah, and remember, lambda, that's my symbol for wavelength. You remember this. First semester, chapter 15. Oh yeah, you totally got this. And this is the frequency. V is the speed. If you don't remember that, I would say go back and take a look at a little of that material back in chapter 15. All that stuff that we learned previously, specifically this equation about the relationship between frequency, wavelength, and speed, is something we will absolutely use going forward. Now, I want you to think about this. So an FM radio station transmits at 100 megahertz. That corresponds to that corresponds to a wavelength of about 3 meters. So the frequency, 100 megahertz, the wavelength, 3 meters. An AM radio station transmits at 1,000 kilohertz. That's about 1 megahertz. So it's less by about a factor of 100. So here's my question. FM wavelength is 3 meters, what is the corresponding wavelength for the AM wave? And I don't want you to solve this by doing a calculation. I want you to solve this by thinking about ratios. I want you to pause the video. I want you to do a quick calculation. And I want you to tell me, what is the corresponding wavelength for AM if the wavelength of FM is 3 meters at a frequency of 100 megahertz? Go ahead and do a quick calculation. I'll be back. Well, as you've calculated, since the wavelength and the frequency are related with this expression right here, frequency times wavelength is equal to c, if the frequency goes down by a factor of 100, the wavelength must go up by a factor of 100. And so instead of a wavelength of 3 meters, AM has a wavelength of about 300 meters. And actually, that's important for thinking about how the antennas work. Now, back to the idea of electromagnetic waves. We have this basic wave. Electromagnetic wave is a wave of electric magnetic fields, as we've seen. And here's a question for you. If that's true, why must your radio antenna be on the outside of your car? And it is. At some point, I mean, when you're picking up radio reception, your antenna's on the outside. It could be buried in a corner of your windshield. That's often the case. Sometimes you can see you have cars that have like little like fins. There's some sort of a little antenna thing on the hood or on the roof or something like that. There's little fins. But you have to have an antenna on the outside of the car. This car with so many antennas on it is an extreme case, but your car has an antenna on the outside. Why is that true? Why must the antenna be on the outside of the car? I want you to think about that. I want you to cogitate. And I want you to actually verbalize or write down, what do you think? Why would that be true? Think back to what we talked about back in chapter 20 when we were talking about electric fields, specifically electric fields and conductors. Go ahead and think about that. I'll be back. And of course, the point is, the crux of the biscuit is this: electric fields cannot penetrate a conducting shell. So since the electric fields can't penetrate a conducting shell, the electromagnetic waves can't make it into the car. And we saw that your car is the safest place in a lightning strike, or it's a safe place in a lightning strike. But also, your car is a place where you can't pick up radio reception. Now, you can pick up cell phone reception. You shouldn't be talking on your phone in the car, but you know that you do, you little scamps. So how is that possible? And that has to do with your antenna to be able to pick up, if you wanted your antenna to be able to pick with the wavelength. Now, that's a point I'll come back to and talk about later. But now I want to talk about AM radio. Now, FM radio, the antennas pick up the electric field. And this thing that sticks out the top, that's the thing that picks up the electric field. It should be about a quarter of a wavelength long. For AM, if you want to pick up the AM radio waves, you would have to have an antenna that's a quarter of a wavelength long, but AM waves are about 300 meters. You would need to have an antenna that was 75 meters long. Well, that's not very practical. So in fact, in an AM radio, you pick up the signal, you pick up the magnetic field component. The electric field component is going vertically. The magnetic field component is going horizontally, and it points along the axis of this ferrite bar, which is inside your radio, and there's a coil of wire wrapped around it. So as the magnetic field changes from going in one direction to going in the other direction, there's a change in flux inside the coil, and as a consequence, you get an EMF in the coil, and that's how you pick up the signal. That's a point I'll show later in a video that I'll share with the class. Now, I want you to recall something from chapter 15. And remember, I am asking you to remember this information, which we talked about previously. All that stuff in the first semester, what do you think I was talking about that stuff for? It's important. I want you to go back and look at chapter 15 and remember this fact right here. Intensity of any wave is just the product, the ratio of the power of the wave divided by the area. So just do a ratio. And I want you to calculate. If I shine a laser pointer on the screen, my question is this. It's got a power of 1 milliwatt. if it makes a spot that's 1 millimeter in diameter, what is the intensity of the light in this spot? And to check yourself, I want you to compare that to the intensity of sunlight on the ground at high noon on a summer day. That's going to be how we can kind of like look at our intensity and see if that makes sense. Now, I actually want you to do this calculation. I want you to get out your calculator. I want you to plug numbers in your calculator. I want you to write down equations. I want you to calculate. I want you to come up with a number for the intensity. I want you to stop and do that right now. I'll give you some time. I'll be back. Now, if we calculate, the intensity is just the power divided by the area. Well, the power, we were told, is 1 milliwatt. And 1 milliwatt is 0.001 watts. The area, of course, we imagine that it's an area of a circle, so the area of a circle is just pi r squared. If the diameter is 1 millimeter, the radius is 0.005 meters. If I square that, put that number in, I get a number of about 1,300 watts per square meter. And that is actually just about the same as the intensity of sunlight on the ground at high noon, 1,000 watts per square meter, which is why the dot of the laser pointer on the screen looks very bright. And it's also why you shouldn't shine the laser pointer in your eye, because shining the laser pointer in your eye is just the same as looking into the sun. So don't do that, but you can safely look at the laser pointer just as you can safely look at the ground when you're outside at high noon on a summer day. Now, the intensity is related to the strength of the electric and magnetic fields, and these equations are ones we're going to use a lot. The intensity is the ratio of the power to the area, but it's also related to the strength of the electric field and the strength of the magnetic field as so. Now, in fact, we're typically going to be given an intensity and calculate an electric field strength. I would do it using this relationship right here. Having calculated the electric field strength, I would calculate the magnetic field strength using this relationship right here. Now, notice the magnetic field strength, which is just the amplitude of the magnetic wave, is given as the electric field strength divided by c, and we know c is big, so what that tells me is that the strength of the magnetic field is small. In an electromagnetic wave, it's typically the electric field that does the heavy lifting, and we will have some calculations that demonstrate this. Now, I want to think about microwave ovens. Inside a microwave oven, which is using waves with a frequency of 2.4 gigahertz, very much like your cell phone, the intensity is 5 kilowatts per square meter. Okay? So inside the microwave oven, there's an electric field, and the electric field will cause the dipole moment of water molecules to rotate and line up with the electric field. But then the electric field switches direction. What? Fake! And so the molecule keeps trying to rotate and line itself up with the electric field. And so as a consequence, this poor little molecule just rotates. It's trying to rotate to chase a field that keeps changing direction. And so it just ends up chasing its tail. It ends up rotating. And the energy of rotation gets converted to thermal energy. And so your microwave, the electric fields in the microwaves given off by inside your microwave oven grab a hold of the dipole moment of those water molecules, cause them to rotate, and as they do that, they deposit energy in your food. That's how your microwave oven works. But here's my question. What's the strength of the electric field? And then also, what's the strength of the electromagnetic field? Now, those are the amplitudes of the wave, the electric field component and the magnetic field component. I want you to calculate both of these numbers given the numbers that you've been provided here. I want you to stop, pause the video, pull out your calculator, write some equations on papers, do this calculation. If you need some help with this, go ahead and weigh in, ask us. Learning assistants and I are standing by to answer your questions, but go ahead and do this calculation on your own, and I'll be back. Now, if you actually do this calculation, we use the relationships that we saw previously. The electric field strength, that is the magnitude of the amplitude of the electric field component, square root of 2 times the intensity divided by c times epsilon 0. And this is that fundamental constant that you learned back in chapter 20. This is the one we've seen before. That's that 8.85 times 10 to the minus 12th number. If you go ahead and calculate that number for the electric field component, you get 1,940 volts per meter. That's actually a pretty large electric field. One of the demonstrations, which I tend to do when I teach this class, is I take a microwave oven, and inside the microwave oven, I put a whole bunch of fluorescent light bulbs. So I'll put a fluorescent light bulb inside there, and then I turn on the microwaves. And what happens is that electric field is big enough to ionize the gases inside the fluorescent light bulb, and the bulbs will actually light. That's a big electric field. And the energy is being dissipated not as heat, but as light in the light bulbs. And they'll stay on for some time. Don't do this. Don't try this at home, okay? But you could. That is something which I can do as a classroom demonstration. Now, next piece of the puzzle, I want to look at the magnetic field strength. 6.5 microteslas. What? That's like about 1/10 of the Earth's magnetic field, which is about 50 microteslas. So the electric field is big enough to light light bulbs. The magnetic field is smaller than the Earth's magnetic field, which we know is actually quite weak. So as a consequence, it's, as we said, it's the electric field in the electromagnetic wave that does the heavy lifting. That's typically true. Now, next piece of the puzzle I want to talk about that slide. So forget this happened, and I'm not going to go back and edit the video to make this happen. Oh goodness, I forgot about it. This is where I play like 30 seconds of stirring music before we go on. Dun, 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 dun. Stirring music, stirring music, stirring music. Okay, we're going to stop. Now, moving on, we're going to talk about the intensity variation for a spherical wave. Remember this equation? Yeah, that was from chapter 15. As a wave spreads out, the waves get weaker and weaker and weaker. The intensity drops as the power of the source divided by 4 pi r squared. R is the distance from the source. And it looks like it's a radius, but it's not really a radius, it's just your distance. If you are standing here and you're at a distance r from the source of waves, the intensity will be the power of the source divided by 4 pi r squared. So let's take a look at this. A cell phone, and your cell phone, if you're talking on it, it emits 1.9 gigahertz electromagnetic wave, very close to the 2.4 gigahertz. That is the frequency of your microwave oven. So it emits a 1.9 gigahertz electromagnetic wave, and the total power is 0.6 watts. Now, if the tower is 2 kilometers away, and it probably is, or it could be, what is the intensity of the wave? And then second, what are the electric and magnetic field strengths at this distance? I want you to take this video. I want you to pause it. So go ahead and stop it right here. Go ahead and pull out a piece of paper. I want you to write down the necessary equations. I want you to do that calculation. If you have questions, I want you to ask. But we're going to pause right here. I'll be back. All right, if you do these calculations, the intensity is just equal to the original power divided by 4 pi times r squared. And if we're 2 kilometers away, that's 2,000 meters. I end up with an intensity of 1.2 times 10 to the minus 8 watts per square meter. What? That's 12 nanowatts per square meter. That is a tiny amount of power. The electric field strength is only 0.0030 volts per meter. 3 millivolts per meter. If I have an antenna that's 1 meter long, it's only going to have a voltage across it of 0.003 volts. Crazy, crazy small potential difference. But the towers are able to pick up that signal. And the magnetic field is like 10 picoteslas. Forget about it. It's doing nothing at that distance. And so what this is supposed to make you understand is how insane it is that with this incredibly low power microwave device in your hand, you can pick it up at a tower 2 kilometers away. That takes some fancy electronics to be able to detect that tiny electric field intensity at that distance, unless you're a shark. Now, I want to think about the electromagnetic waves again, and I want to talk about specifically the idea of polarization. And before I do this, I want you to pause right here, and I want you to take a look at a video. And along with the lecture, I'm also going to post little videos of the day. I want to post one about electromagnetic waves and polarization. It's me in the studio, and I do a couple of demonstrations, and it introduces you to the idea of polarizations to make it more real before we go on and do the next part. Because the next part is talking about polarization. Now, we talk about this in the book, and we say the plane of polarization is the plane in which the electric field vectors lie. And we talk about in the textbook how if you pass an unpolarized wave or unpolarized light through a polarizer, it causes it to be polarized along the axis of the polarizer. And then subsequently, if I have another polarizer at an angle theta with respect to the first polarizer, only some of the light passes. And the amount that passes is given by this relationship right here. The incident intensity times the square of the cosine of the angle between the two polarizers is equal to the transmitted intensity. Now, I want to talk about AM radio for a second. And it turns out AM radio, when it comes to you, has its electric field oriented vertically. The magnetic field is oriented horizontally. So as the wave is coming towards you, it looks like that, and then sometime later the electric field is down, the magnetic field is in the other direction. So as the electromagnetic wave is coming towards you, you have a variation of electric and magnetic fields. The axis of the antenna, it's this ferrite bar, has to point parallel to the ground because there has to be a change in flux inside the coil that that bar is wrapped around. So as a consequence, if you take your radio and you turn it at a 90-degree angle, you don't get reception, as we saw. Now, it turns out the sky, when it scatters light, and we'll talk about scattering later, the sky light is polarized, particularly if you're looking at the sky, if you're 90 degrees to the sun. And actually, if I take these vectors, the polarization vectors, right here, the axis of these polarizers, the one where you're able to see the light, it points in the direction of the sun. And so bees, their eyes actually detect the polarization, and they can use this to figure out where the sun is in the sky, which is kind of a crazy thing. And they do that because in their eyes they have these little rhabdoms, these sensing cells. They're kind of like they're made up of these individual little units around a central core. And the molecules that sense the light, the pigments, are preferentially aligned along the axis that points like these arrows that I've drawn. So as a consequence, you're much more likely to pick up the light if the electric field is along the axis of the rhabdom. So if electric field comes in polarized that way, these two will pick it up. These ones won't. And so the bees, by telling the differential intensity that they're detecting in their little units, are able to detect the polarization of light and use that to figure out where the sun is in the sky. And I have a little video that demonstrates that, how bees use sky polarization to navigate. And it's something that we made for kids, so it's a little simplistic, but you'll get the idea. It's kind of a very, very cool thing. Now, I want to talk about long wavelengths that come off of objects because they're warm. And we talked about this in the first semester. We talked about the energy radiated by warm objects. Remember, we had that thing of like Q over delta T is equal to the emissivity times sigma times A times T to the fourth. Remember that? That was like back in chapter 12. Well, if you don't remember that, I want you to take a moment. I want you to look back at chapter 12, and I want you to remember that. This is one thing which we'll use repeatedly right now. We'll use the energy emitted by warm objects. But now I want to talk about the wavelength. And it turns out the wavelength, the peak wavelength of a warm object varies with temperature according to this relationship right here. The peak wavelength is proportional to 1 over the temperature. So as a consequence, if I have hot objects, they emit short wavelengths. And if I have cold objects, they emit long wavelength. Everything emits. Hot objects emit more, and we know that there's a very strong dependence. But also, hot objects emit shorter wavelengths, and that's going to be an important part of our story. I want you to do a quick calculation here. A typical incandescent light has a filament that operates at 2500 degrees Celsius. So if you look at the hot filament inside here, that's how hot it is. question, what is the peak wavelength of the emission? And I want you to do a calculation and figure out what is the peak wavelength for that emission. I want you to take a minute, do that calculation. I'll be back. If you do this calculation using Wien's law, you get the peak wavelength is just 2.9 times 10 to the 6 nanometers times Kelvin divided by the peak temperature, which of course I have to put in Kelvin, so that's 2773 Kelvin. I get a wavelength of 1050 nanometers. Now the crazy thing is, this is in the infrared part of the spectrum. It's not in the visible light part of the spectrum. And that's why incandescent light bulbs are so terrible. It's not the fact that they're not giving off a lot of radiation. If I have a 100-watt light bulb, it's giving off 100 watts of electromagnetic waves, but most of it is in the infrared. Only 4 watts is in the visible light part of the spectrum. So they're terrible. And they're not terrible because they're not giving off 100 watts. They're terrible because they're only giving off 4 watts of the stuff you want, the visible light. And the reason is they're just too cold. To be able to make the peak wavelength be in the visible light part of the spectrum, I'd have to make the temperature much higher. And the only way I can make the temperature much higher is to use something other than a metal. Metals can only get as hot as 2500 degrees Celsius. The surface of the sun is approximately 6,000 Kelvin. And at 6,000 Kelvin, it's hot enough that the wavelengths that you get are in the middle of the visible light spectrum, as we know. Now, we have a little video, too, of this part of the Little Shop of Physics collection that shows if you have an incandescent light bulb, it's giving off some visible light, but ridiculous quantities of infrared. Now, when you emit electromagnetic waves, it means that you emit energy. And as again, we talked about this in Chapter 12. Remember this basic relationship. And remember Q over delta T, that's just a power. So warm objects emit thermal energy. For instance, this seal has a patch that's called a thermal window, and the seal makes one patch on its body really hot, gives off a lot of electromagnetic waves, and so it's using that to keep itself cool. And there are animals that can sense this. Pit vipers have this second vision organ, and rattlesnakes are pit vipers. They have the second vision organ right here that detects the emitted thermal radiation, and so a snake can see you in absolute darkness using radiation that you emit, which is a crazy, crazy thing. Now, I want to do a couple calculations for you. You have a surface area of about 1.8 meters squared, and your emissivity is about 0.97, and that's regardless of your skin color. We all emit the same. We all have the same emissivity. We're basically all made out of the same stuff. But my question is this: how much power does your body radiate away? And that's using that relationship from Chapter 12. And then second, what is the peak wavelength of the emission? I want you to pause. I want you to do a quick calculation. When you finish with that, you can start the video back up. I'll be back. If you do this calculation, the energy that you emit is just given by this relationship right here. Q over delta T is equal to the emissivity times sigma times A times T to the fourth. Remember, the sigma, that's that fundamental constant. You can look back and figure what that is. That's 5.67 times 10 to the negative eighth. And then the peak wavelength is given by this relationship right here. You radiate about 870 watts. That's ridiculous. So you're radiating incredibly brightly, but the wavelength that you're radiating at is about 9,500 nanometers. Now, visible light runs from about 400 nanometers at the blue end to about 750 nanometers at the red end. So 9,500 nanometers, you can't see this. The snake can, but you can't. That's far too long a wavelength for you to be able to detect with your vision. So the snake can see you, but you can't pick other people that way. And the snakes do it by using these vision organs called pits on the front of their face. And so the snake can see you if it's blindfolded. A snake can see you in the dark because the thermal radiation you emit comes into the pits, and it can detect where that radiation is coming from and even can make a rudimentary image. These pits are hooked up to their visual cortex. And so if the snake senses your emitted thermal radiation, it actually sees you that way. It's a fantastic thing. And so that's why snakes, which tend to be the same temperature as their environment, like this snake right here, can sense warm-blooded creatures like this mouse right here, which is warmer than its environment. And you can see how if you're a snake, this is a very effective way to sense creatures in the environment. Now, the next thing we're going to talk about is other kinds of electromagnetic waves. And we began by talking about the fact that if you're talking on the cell phone, you do have electromagnetic waves from your cell phone that are going through your head. And you are absorbing radiation from your cell phone. Will talking on the cell phone give you brain cancer? No, it won't. And we're going to talk about why next time. Enjoy the rest of your day, and thank you for joining me for this first installment of Physics in the Time of Social Distancing. Take care.